Okay, so now I'm going to talk about a little bit about experiment one, the nuclear experiment that you guys are going to be doing this week. And I just wanted to give you kind of a few hints and tips on how to do this. It is about material that we covered previously in the nuclear chapter, uh, but it's kind of a more involved problem basically that you're solving. So I'd like to talk a little bit about that. So this is the online version. Now, if you already have your lab manual, like some of you will this week, you'll have these pages here already. I just put sample data in. There's also videos that you can watch. So this video will show the experimental procedure. They basically do the same thing as described here. It's a little bit different. They don't weigh there's more potassium there in their sample than there would be. We have, in this experiment, it calls for about 1 gram of potassium chloride. This is a really cool video too, which is optional, but it shows some guy going and measuring the radioactivity of a pallet of bags of potassium chloride. So if you're standing next to a bunch of potassium chloride for a very long time, you could get a significant dose of radiation. It's not that bad. The half-life is really long. So if you take a look, you'll want to read this experimental procedure, but what's really relevant is right here and also what's underlined. So in the potassium chloride, it contains a certain amount of the radioactive isotope potassium 40. Its abundance is only 0.012%. So that's going to be important because out of all the potassium atoms that we have, only 0.012% of them are going to actually be undergoing a nuclear decay process. It does undergo decay by actually several different types of decay processes, including beta emission, electron capture, and positron emission. In the pre-lab exercise, you're asked to write down nuclear equations for its radioactive decay processes. You want to write equations for these 3 processes. So it's actually surprisingly undergoing beta emission and electron capture and positron emission, which is unusual. Usually, it's one or the other, as we had described in the lecture, but it can undergo all 3 of these. What we're trying to do here is, in this experiment, if you were to come into the lab normally, you would be making a measurement of the radioactivity using a Geiger counter and the number of radioactive events that reach the Geiger counter per minute. However, potassium 40 has a half-life of 1.28 times 10 to the 9 years. So it's a very, very long half-life. And obviously, this is so long. So how do we know that the half-life is this long based on just measuring the radioactivity for a much shorter period of time? And the answer is that, well, we can extrapolate based on what we observe to how long it would take for half of the potassium in our sample to be gone. So here is the rate law for the nuclear decay process. It's first order. NT here indicates the activity, which is the number of the number of decay events per minute. So and so that's what you're measuring in this experiment. It's not very many, as you might imagine, even though there are many potassium 40 nuclei in a sample. Not many of them are actually going to decay in this short period of time. And so that contributes to the error in this experiment, that we're only measuring over a period of a minute. We do it 3 times, but only over the period of a minute. And this thing has a half-life of 1.28 times 10 to the 9th years. But what you'll find is that even with this short measuring time, we can get a fairly accurate measurement of the half-life of this potassium 40, and that's what this experiment is going to be all about. Now, a couple of notes, important notes here, going back to the beginning. So what's really, really important here, number 1, is that the abundance of the K40 is only 0.12%. 0.012%. This is really important. We're going to have to factor this into our calculations. Also important is that of the radioactive events that are occurring, our Geiger counter won't be able to capture all of them because the particles that are spit out go in every which way in every direction. So only about 1/70th of the radioactive events will be measured. So however many radioactive events that we actually observe, we're going to multiply those by 70. If we use the real Geiger counters in the lab, they all have a multiplier factor, which is around 70, but it's been calibrated to be exact for that particular Geiger counter, up to 3 sig figs. And so we're going to have to use both of these pieces of information in our calculations when we do our calculations later. So what would go on in the experiment is that you would put the Geiger, you would weigh out, first of all, you'd weigh out some potassium chloride here in a beaker. You subtract out the weight of the empty beaker and you'll get the mass of potassium chloride. So that mass is going to be around 1 gram. And then we're going to take the Geiger counter, and without the potassium chloride near it, we'll measure what is the background radioactivity in just a normal atmosphere. We are always being bombarded by radioactive particles, by particles that are resulting from radioactive decay. And so we can count that. That's the background radiation we have. And here's the sample data I provided. These are counts per minute, so radioactive events per minute. And so we have 2, 22, 26, 18. These are realistic counts based on what I've observed in the lab when we do this experiment. And then we put the Geiger counter, the sensor, directly above the potassium chloride, like you'll see in the video. And we get the potassium chloride plus background radiation. Okay. And so to get the actual radiation here, we're going to average the background activity and average the background plus KCl. And the difference will be just the radioactivity of the KCl. Okay. And so it says, how do you calculate the true activity of your sample? Well, they talk about it here, and I was just describing it, but I think part of the pre-lab is going to be to make an equation that describes this. So let me go to the pre-lab where right here. So it says, write mathematical equations that will show how you calculated the detected activity. And they have some like basically notation that you can use, okay? So the detected count rate from your sample minus the background radiation. So like I said, we're going to average our background radiation. We'll get a count for background radiation, and then we'll have the total, which is the sample and the background. To get R, the sample and the background, we're going to have to take the total, which is going to be the radioactive potassium and the background, and we're going to have to subtract out the background. Okay, so that will be R. And then not only that though, but R is only the ones that reached our detector. So our R true is going to be 70 times our R, or 70 times the total radiation minus the background radiation, like that. And so this is what we're going to use. We're going to get R true in this fashion. And that's how we're going to get it from our data. So let's go ahead and apply that in our actual calculations here. So going back up here, calculating the true activity of potassium. So what you're going to do is you're going to apply that equation basically, because our multiplier here is 70.0. So we're going to use that. So our R true, and I'll call it R true. And this will also be that the notation they use in the actual write-up, the true activity is NT. N sub T. So that's a different notation than they used in the pre-lab exercise there, but that's what we're trying to get. And this is going to be 70.0 times the radiation of the total radiation, which we're going to get, that's going to be our average right here. So this right here is going to go right there, minus our radiation from the background, and that's going to come from right up here, the average of the background activity. And so that will give us our true activity, or what's the NT here. And then it says a kind of separate problem is calculate the number of radioactive potassium-40 nuclei in the sample. Well, you're going to have a mass of the potassium chloride. And so I'm going to call that, I'm not going to calculate it for you. I mean, it's pretty simple to calculate, but you're going to have blank grams of the potassium chloride here. Blank grams of the potassium chloride. And, and so you're going to have to now convert that to a mass first of potassium atoms. Okay, a mass of potassium atoms. And so first, or sorry, a number of potassium atoms. So first we're going to have to take this and we're going to have to find out how many of these that we've got. Now there's different ways that you can do that, but we're going to take this mass of KCl. So it's, where's the average mass? That's going to be right here. I'll use a different color. Right here, that's going to be going down here, right in there. It's going to be our grams of KCl. Okay, and we're going to now have to convert that to what we want is a moles of KCl. We want a count of these things. Okay, how many? So what do we need to do that conversion?
The molar mass of KCl, right?
Yeah, we're going to need the molar mass of KCl. So let's go ahead and calculate that. I've got the periodic table behind me here. So for the potassium, it's 39.1. 39 point. I'll use all the sig figs I have here, I guess, just to be extra safe. I probably only get like 2 at the end, but 39.098 grams plus the chlorine, which is 35.45 grams. And that's right here. So we'll calculate that. So that's going to be our molar mass here. 39.098 plus 35.45. I'm just going to actually write this up to this point. Wheel at 4 is fine for sig figs. I'll call it 75.548, and just for the sake of saving room, I'll call it 75.55. So 75.55 grams of KCl is 1 mole of KCl.
Mr. Lemieux, it's
Yeah.
74.
Oh, whoops. Oh, yes. Thank you. 74. Whoopsie. Okay, 74. Thank you. All right. Appreciate that. Okay. So now we've got the moles of KCl, and we can see from the formula that in 1 mole of KCl, we have 1 mole of K atoms. Okay. Now we could also convert this to the number of K atoms first, and then say there's 1 K atom per KCl. That's fine too. But at this point, we're going to want how many potassium atoms we have. So a mole of potassium, or a mole of anything, is 6.022 times 10 to the 23 of those things. Here we're talking about K atoms. And then finally, going back to the write-up, Well, we were given a fraction or a percentage of all of the potassium atoms that are potassium 40 atoms. And that was 0.012%. But we want to get this as a fraction so we can multiply it by our number of Ks here. And so we can divide that by 100%, 0.012%, divide by 100%. That will get rid of our percents and give us a decimal here. And that decimal is 0.00012 to 2 sig figs. So eventually we'll have 2 sig figs on this thing. And so the way we use that is we say, well, for every 1 potassium, there is 0.00012 potassium 40s. And that's going to tell us how many radioactive potassium 40 atoms that we have. And so I'll leave the punching up to you, but I think that that's where most students get stuck on this one. So yeah, that will give you your number yeah. And so, and I want to make a correction here. I said NT. Sorry, this is our NT. Man, I messed up. Sorry about that. But this is going to be our number of radioactive molecules. This is our rate. This is going to be in counts per minute. So 1/minutes. Sorry about that. This is the rate. R true is the rate here. And the NT, what that represents is how many radioactive atoms that we have. So now we can use this to get K because we have that the rate equals the K times the number of radioactive molecules, where K is the decay constant here. In terms of units, the rate is in basically K40 events per minute. We usually leave off the K40, so you could say K40s per minute. All right, and the NT is how many K40. NT is how many K40s we have. The unit for the K is counts per minute, or 1/minutes. Now, a lot of times people just leave off the K40, so it's just a count and they don't give it units, but we're talking about radioactive events per unit. So our K can be, is in rates of 1/minutes, okay? So when we calculate the decay constant here, it's important to note that this decay constant is going to be in minutes, but your half-life is still in years. So you're going to have to make those mesh with one another somehow. And so here to calculate K, what we're going to do is we're going to have K equals the rate over NT. And NT is going to be very big number. The rate is going to be small. It's going to be like 20 or something. So it's going to be, about 20 to 30-ish. And this NT is going to be, times 10 to some kind of big number. I think it's 14 or 15-ish down here. So you're going to get a very small number. K will be small, in the, negative 14, 15-ish type of range. And what's important though is the units are 1/minutes. So K has units 1/minute. Okay. So the problem is that now for the next part, what we want to do is get the percent error. But to get the percent error, we need to have, we're going to get the half-life here. So let me go ahead and get the half-life. I should have done that first. So now we have a K. So remember that the half-life that we get is going to be the natural log of 2 over K. But that's going to give us a half-life remember K has units of, remember, right now at least, it has units of 1/minute. So our T1/2 is going to be some blank minutes. Okay, so you're going to have to, in order to compare this to the true, well, let's go back and look at what was the true. So the true was given to us at the beginning. Let's scroll back.
It was 1.28 times 10 to the 9th years.
Yes, that was it. Just to kind of point out where it is, it was right here. So they gave us the half-life. 1.28 times 10 to the minus, or 10 to the positive 9 years. Like, you know, 1.28 billion years. Really long time, half-life, this one. It decays very slowly. So we'll write that there. 1.28 times 10 to the 9th years. So our half-life is going to come out in minutes, and we're going to have to convert that to years before we can compare them. So the first step will be to take our blank minutes that we get for the half-life and to convert that to years so that we can compare them. So so we know units of minutes go here, right? So we could say 60 minutes is 1 hour. So we convert to hours. Then what might we convert to?
When do we go from today's and then to?
Yeah, we can go 24
Can you go
hours.
from days straight to years?
Sure, you could, if you have the right conversion factor. I don't know what that is. I don't have it off the top of my head, but you could look it up, yeah. If you wanted to do it step by step, convert 60 minutes, 1 hour, 24 hours, 1 day, and then 365 days is 1 year. And so that will give you a half-life now. So now you'll have T1/2 is going to be blank years. And at that point, you can take this and you can put it right in for the experimental. And the true will be the 1.28 times 10 to the 9th years. You put those in there and you can calculate your percent error. And the percent error isn't always great. And I tried to make sample data that kind of reflects the real life of trying to do this experiment, because you're only counting the counts over a period of a few minutes. Let's think about error in this experiment. I mean, your net counts is somewhere in the 20 to 30 range. And it looks like you've barely got like 1 to 2 sig figs. So chances are, if you get like the first, you should probably get the first sig fig right. So like, let's say you kind of carry out your calculations and you get that your measured half-life was like, 1.9 times 10 to the 9th years. That's pretty dang good, right? Or if you got, 7.63 times 10 to the 10th years. That's not bad, considering we have 2 sig figs in this measurement right here. Our measurements that we're doing right here have at best 2 sig figs, but just barely. And so to get an answer with 1 to 2 sig figs right, perfectly good. Okay. And then you have some related problems that you could probably do, you should be able to do based on what I showed you. In discussing error, I just talked about it, right? So the fact that we're only counting over a very short period of time, we've got a lot of background counts. You can see our data is not very precise. It's kind of bouncing around, totally normal. This is kind of a random process, radioactive decay, and we're taking such a narrow snapshot of it that we don't have a whole lot of sig figs here. just a note about error. A lot of these experiments as we go forward will ask you about error. Error is not a mistake. That's not what we're talking about. Mistake is one thing. Error means the limits of the accuracy with which you could actually realistically measure this thing given your experimental procedure and the equipment that you're using. So we can see here, given our experimental procedure of only counting radioactive decay events over 1 minute, due to our very short time frame, we get imprecise data, good to maybe 1 or 2 sig figs. So that's going to be the main contributor to your error. Other contributors to your error could be just that basically the calibration of the detector itself can be quite difficult because, again, we're only measuring over a short period of time. And there's also the possibility that the detector not being calibrated well or not capturing all of the radioactive events. But the main contributor is the fact that we're just making this measurement of over a short period of time for something that decays with a half-life of, a billion years. So it's pretty amazing that we can even make this measurement to 1 or 2 sig figs, given that very, very short period of time that we're measuring the decay events. And then when you're calculating the half-life, why is it important to include the abundance? It's because not all the potassium atoms are going to be undergoing decay, only the potassium 40. So we need to be counting only the atoms that may actually undergo this decay process, not all the other stable nuclei that won't. The remainder for the pre-lab is just a bunch of terms which you can get from your textbook and the write-up here. And the 3 nuclear equations that describe the 3 decay modes, they told you at the beginning what those decay modes are. They want you to write, let's see, these right here. Radioactive decay by beta emission, electron capture, and positron emission. Write all of those nuclear processes for potassium 40. And so that's going to be my tips for you for experiment 1. I hope that helped. Like I said, I did make the data to be not perfect, so it'd be more like real data that students got in the lab. So you may find that, you don't get a perfect, percent error that's 0%. Your percent error won't be perfect. Sometimes I get percent errors are quite significant in this lab, like 50% error, not unheard of. But that's what happens when you take a measurement that's only good to 1 or 2 sig figs. Is when you have only 1 sig fig, probably the best you could hope for is 10% error. If you have 2 sig figs, you can get as good as 1% error. Yeah. And so, yeah, those are my tips there for experiment 1. I hope those help, and then you guys can ask in office hours if you've got questions. Okay. Let's stop the recording there, and we'll continue with office hours.